let's prove a set identity using element chasing. So we're going to prove that for any sets A, B, and C, it's always the case that if you take the union of B and C and intersect with A, it's the same as intersecting A with B, intersecting A with C, and then taking the union of those two. And so we're going to do this by element chasing, which means that, so first of all, we're going to do two containments. We're going to show that every element here on the left is on the right, and every element on this right set is on the left. And we do that by element chasing, which means we take an element here and show through logic that it needs to be here also, and then we're going to take an element here and show through logic that it needs to be here. So the first step, let's say you're writing the proof, the first step is always to announce how you're going to do it. So we prove both containments. So we're going to prove both containments. And then it's good to indicate how you start. So let's start with this containment. Let's start by showing that everyone on the left set here is on the right. So how do we do that? We first take an arbitrary element on the right. So let x belong to an arbitrary element of the left. So let x belong to A intersection B union C. And we want to end up showing that then x is going to belong on the right here. So let's see what this means. So if x belongs to A intersection B union C, then by definition, x belongs to A, right? And x belongs to B union C. So this is just the definition of this intersection here. Okay. But then by definition of union, so if x belongs to B union C, then x belongs to B or x belongs to C. So again, we use the definition of intersection, we use the definition of union. So what we know now, so we know that x belongs to A, and also that x belongs to B or x belongs to C. So we know that it belongs to A, but also it has to belong to B or to C. So we have two cases essentially. So if x belongs to B, then x belongs to A intersection B. And if x belongs to C, then x belongs to A intersection C. Therefore, x belongs to A intersection B, or, so again, our two possibilities, or x belongs to A intersection C. But then by definition of union, if x belongs to A intersection B or A intersection C, then x belongs to A intersection B union A intersection C. Okay, and this proves the first containment, right? So we showed, so let's look at this carefully. Let's revise this actually. So we want to show equality here, and we start by showing that this set is a subset of this set. So every element here is an element here. How do we do that? We take an arbitrary element here, so let x be on the left-hand side, and we show, we're going to conclude that it's on the right-hand side. Now, how are we going to do that? This is one of those places where it becomes very clear that you need to know the definitions. If you do not know the definitions of set equality, containment, intersection, and union, it's impossible to write the proof because you need them at every step of the proof. So always you need to review the definitions. You need to know that you know them. If you don't know them, you need to go and know them because it's impossible to write the proof without them. So let's start with this containment here. So let X be an element on the left-hand side. So X belongs to A intersection B union C. So then by the definition of this intersection here, that means that X belongs to A and X belongs to B union C. So X belongs to A and X belongs to B union C. Okay, let's look at this right part. If X belongs to B union C, then X belongs to B or X belongs to C. Again, that's the definition of the union. So what happens? So we know that X has to belong to A, but also it either belongs to B or belongs to C, right? And of course, this is the inclusive or, so it can be both, but it belongs to B or it belongs to C. Okay, so you have two cases. It's in B or C. Now, if X is in B, then X is in A intersection B, because X is always in A, and so if it's in B, then it has to be in both. Now, if X is in C, since X is always in A, then it also has to be in both. So these two cases here are just telling you that X has to be in A intersection B or in A intersection C. Those are the two cases. But then by the definition of union, X has to be in the union of these. And so X is on the right-hand side. So that means that every element on the left has to be on the right, and that's one side of the containment. And so now we need to prove the other side of the containment, so the other direction. So we need to prove this direction here. We need to show that every element on the right-hand side here is also in the left-hand side. And so again, let X belong to the right-hand side. So let's write it here. Union A intersection C. So what does this mean? Again, by the definition of union, then X belongs to A intersection B, or X belongs to A intersection C, right? Okay, now what does that mean? That means that, so there are two cases. X has to either belong here or X belongs here. Okay, so if X belongs to A intersection B, then X belongs to A and X belongs to B. And the other case, if X belongs to A intersection C, then X belongs to A and X belongs to C. Notice that in either case, so in both cases, in either case, X belongs to A. So it's always the case that X belongs to A. And of course, in either case, it's also in either case, if you look at both cases, it's also the case that X belongs to B or it belongs to C. So what this means, so therefore, what this means is that X belongs to A and X belongs to B union C by the definition of union here. And finally, by definition of intersection, what this means is that X belongs to A intersection B union C. And so this finalizes the second containment, right? So with this, we show that if X is on the right-hand side, then it's also on the left-hand side. So now, since we showed both containments, so we showed that the left-hand side is a subset of the right-hand side, and the right-hand side is a subset of the left-hand side. So here we can conclude, so since both containments hold, we conclude equality. So we conclude that those two sets are equal.